Alright, it's good to see you guys today, and I hope you're enjoying your post Pi Day celebrations here. This is a little anticlimactic. Normally, if we were to, normally I do like to show some of those. But I send out some Pi Day videos. Hopefully you saw some of those. They're exciting, you know. We are going to just move on, though, too, here. So at least you get to eat while we do math. Is that all right? Good compromise. So thank you to those who brought in some various round things. I think almost everything really was round here. That was pretty good, right? Everything not round at all. I think everything was round. That's pretty good. And I'm sorry I didn't win the pie eating contest for those who cheered me on. I was so close. Mr. Getz edged me out. Just edged me out. They crowned someone for the ladies. And her name is Miss Payne. Maybe. I don't know. We should review the footage, really. I would like to think so, yes. But it all comes down to the wire, you know. All right, let's have my three favorite students here. These questions, are you ready? Don't come up. Just tell me what you got, and we'll all tell you whether we think you're right or wrong. Varun, can you answer any of these? Which one? 3 minus 14i. Can you confirm or deny someone? Cassie, can you take the second one? 3 minus 4i. Can I get an amen on that one? Yeah? Theo, did you get the last one yet? That's the hardest one, probably, out there. Is it 8? I don't know. Class, what'd you get? 8? These people up here did not get 8.
Okay, look, I messed up at first.
It is 8, though, I think. Yeah, just be careful, is all. Just be careful. I mean, it's not... But it is also kind of surprising in the end that you just get that, seems like that should be nasty thing we started with, and in the end you just get 8. That's really kind of wild that that comes out. So check your work again if you're not getting 8. It should come out that way. You know, multiply the two binomials maybe first, and then multiply again by a third. So there's a little bit of algebra to do, but I trust that you can do it. That my trust might be misplaced. So good job, people who did the work. This does raise an interesting question, doesn't it? There are things that when you cube them are 8, like 2, right? 2 is an obvious thing that when cubed gives you 8. We call 2 a cube root of 8, right? But we expect, perhaps, maybe we just never really talked about it. Don't we kind of expect there to be 3 cube roots of 8? Right? I mean, you know, I'm just talking about, like, for the polynomial x cubed minus 8, don't we expect 3 complex zeros by the fundamental theorem of algebra? X cubed minus 8 for that polynomial. 2 is a 0, but shouldn't there be 2 other zeros as well? Well, one of them is this cube root right here you're looking at. So this is just like 2. This is another cube root of 8. Yeah.
Something interesting, you take the -1 and the 3, you add them together, you take the square root, you get 2. 2 cubes of 8. Does that have something to do with it?
Maybe, yeah. We'll see where this goes today. Yeah. Yeah, I mean, there's certainly some theory to work out on this, not just kind of like, oh, look what happened. There's definitely some theory to talk about as well, that's for sure. But overall, is this a nice review, these first couple problems? And if you keep going, that's great too. I'd like you to try some other ones too. I thought I'd open class today by showing you a picture of a table card, a name card that I got at a wedding. This was at Mr. Davis's wedding. Not most normal people probably wouldn't have this as their table number at a table wedding, but at Mr. Davis's and Mrs. Davis's wedding, Mrs. Davis is our theater person, but formerly an English teacher here at RM. So the guests of the bride had English clues, and the guests of the groom had math clues. So what table did I sit at? Yeah, I sat at table -1. That's true. A true story. This is a scanned copy of my.
Stated that you can never have negative numbers of physical objects. I am
some
now
of
wrong.
the English tables had table names. They weren't even numbers, right? So it was fine that it was -1. And all the guests, I think he gave harder problems to some of the math teachers who were in attendance. I think to the groom's guests, they got really, really simple math problems. Not for like, you know, Uncle Joe probably didn't get I to the 6, but you could have handled that, right? I to the 6, you could have handled that. So this seems to come out of the blue to like be thinking about complex numbers. Seems like a completely like reversal, switch gears. Like, what are we doing? Were we in the middle of polar stuff? Well, hopefully even before we leave today, we'll start to see the connection between the two ideas in an important way. So before I don't want to, just because it's a half day, we're not going to do the rest of these. I'd like you to still, you know, give them a try just to review a little bit. I do want to just give you a few pointers though that normally I would let you kind of like think through again on your own, but I just want to remind you of how to handle this. Can you handle the I to the 30th? Any discussion needs to be had there?
Yeah.
Okay. All right. What about in D and E? How do we handle division? Remember the task for all of these. The task is in the end write these in standard form. A plus bi. That is something plus something I. Right. So how do you handle this situation where you're dividing? Can anyone jog our memory a little bit here? Yeah, what do I have to do? Can you actually give me instructions on D? Like what the first step would be? We won't work it out, but.
Multiply like by 2 plus I over 2 plus I.
And I think that will make the denominator real then. Well, just see how that goes for you. If you don't remember how that feels, as you do it, you'll be like, oh yeah, I do remember doing this, I think, and I'll just do it. Maybe, right? Maybe give it a try. And in the end, you'll know you're successful if you can write your answer as something real plus something real times I for every single one of these problems on the whole worksheet, right? Something real plus something real times I. Okay? Again, I don't want to dwell on these problems though because we have kind of a half day and we want to talk about some of the newer conversation to bring in. Okay. So let's open this discussion with these two questions. Where does a number like 1 plus 2i live? Is it somewhere in between like 1 and 2 on the number line? Or where I don't know how this works. Or here's another question of a similar vein. Which one is bigger? If you were to desire to put a less than or a greater than sign in between these two complex numbers, how would you assign the direction of that inequality? Have you ever thought about these questions before? Ian, all right, how many comments you get today? How about 3 in the next
This is
2
the
minutes?
third one.
This is the third one?
Yeah.
Okay, all right, then
The case with the first one
Hold on,
is
wait.
impossible on a horizontal number line. However, adding a vertical axis allows you to plot complex.
Yeah, that's our strategy. This is the number line, or sometimes we call it the real number line, right? So obviously a number that isn't real doesn't belong anywhere on that line. And we have another device for visualizing.
I have no idea how to assign value.
Yeah, the answer is the second one is kind of nonsense. The complex numbers do not form an ordered field of numbers. So, yeah.
No, I was just, my question was going to be, isn't it not real?
Yeah, exactly. The answer is like both questions are kind of nonsense, right? So yeah, we can at least do the first task. We can visualize the complex numbers nicely by adding a vertical axis. So the real number line, which you see up here, which you grew up with like even in elementary school, is embedded in the complex plane. And to visualize a number like the ones we've been working on in the warm-up here, right? We always get something plus something I. We can represent the real and the imaginary parts on the two horizontal and vertical axes. And then the point is not just kind of an abstract idea, we've kind of made it concrete, right? So in that sense, the number I, there's nothing like imaginary about the number of I, it's just the point 0, 1 on the coordinate plane. So I would just be like that point right there. Okay. Really, what we're saying is, this is good, right? On the heels of stuff we've just been doing in the last unit too. What are complex numbers? Really, they're just two-dimensional numbers, right? They're just numbers that have 2 components to them rather than 1 component. Okay. So again, this is called the complex plane, or sometimes it's called the Argand plane. We have a couple different new words for you today. We can talk about the magnitude of a complex number. We might not be able to put them in order, right? But we can at least say how large they are in some sense, kind of. And the magnitude would be, well, what would that be? I think we've done this before in other contexts. This is just like putting a different gloss on it. But how would we compute the length of that segment from the origin to the complex number z? Yeah, I think we've read this book before, right? And it makes sense, I think, still to use this notation, these vertical bars, that kind of in our minds now, hopefully, you understand those to mean magnitude. Sometimes we also call it the absolute value of the complex number. Or would you like a third word? How about modulus? So 3 words. I knew you wanted 3 words for that. For the length of a complex number, right? Kind of is the idea. And I think I've already used this word, but whenever you're talking about, this is the only form probably you're used to, coming from algebra 2. We would call the form you're used to standard form. That is something plus something I. Something real plus something real times I. It's called standard form. Or, given our new imagination, a new visualization of this, we might call it rectangular form too, because we're using the rectangular coordinate system to describe a complex number, right? That's a good word, and it also sets us up for the other thing we might do today, and that's to describe them in what form? Where are we going to take this? It's in the title. Yeah, we're also going to describe it in polar form. So you can see why we might like to say that this is rectangular form, just to set ourselves up for the fact that we might also like to represent them in another way, and we'll do that in a minute here. So, I think this is an easy enough task on the heels of what we've just described. Sorry, lots of new words. Can you plot and then this number right here, 8 minus 69, and also find its magnitude? It's in my right desk there, 100%. Really use words on it.
When you give us something that you haven't known that
Square imaginary numbers.
See? Yeah, I think almost every mathematician would tell you that we all regret in the history of mathematics the fact that these are called imaginary numbers. I mean, really, you should go either one way or the other. Either all numbers are like fully concrete and real, or you could also make the claim if you're a philosopher that like all numbers are imaginary. Like in what sense can you like show me the number -3 or something like that, or even the number 3? Like what does that mean? Like the number 3, you can show me 3 of something, but the number 3 is like an imaginary thing that we like project meaning into the world on, you know. So the point is like, is this there's nothing imaginary about these. In fact, now we even have a way of like putting our hands on them, right? There's this number we're talking about. What's its magnitude? Did you find it? Yeah, it comes out nice, doesn't it? I made this a Pythagorean triple. A lesser known one though, right? Does that come out to, it comes out to 17, I think, is what you'll get. I don't know. Maybe you wouldn't know that without a calculator though. It's good. We should like practice other Pythagorean triples besides like the 2 or 3 that we see all the time. It's good for us. All right, let's talk about polar form. There are no real surprises here. We're just going to swap our x and y out for our cosine theta and our sine theta, right? So here we go in polar form. We'll make the substitutions, again, unsurprisingly. Instead of x plus yi, we have x is our cosine theta and y is our sine theta. And then I think it would be a good choice to factor out the r, maybe, is I think usually a choice we would make. And this is really just the same as what we had earlier. It just reveals what r and theta are if you write it in this form. Okay. Sometimes, because as you write these, you'll have many, many opportunities to be writing numbers, complex numbers in polar form. And it'll get a little old to be like 5 cosine 30 plus I sine 30 or something, right? So, because this will always be like the same thing you're writing. So sometimes we just write this too. So you're welcome to use that shorthand if you understand at any time. If I grill you on like, what does that mean again? You can tell me immediately that's really what you mean. Never use a shortcut that you don't fully understand. But if you're getting tired of writing the thing in the yellow box, you're welcome to just say instead of r cosine theta plus I sine theta, you can say r cis theta. Do you understand what that stands for? Cosine of theta plus I sine theta. Okay? So just keep in mind at every moment I should be able to like man on the street interview. What does that mean again? Right? Like don't like just use it blindly. Okay. And then as always, of course, r is the magnitude. Here's one more, right? R is the magnitude we've just been speaking about recently, right? The magnitude or the modulus. And theta is the angle, you know, up to whichever quadrant it needs to be in, right? You find it the same way we always do. And let's give you one more word, too. Sometimes we call the angle the argument of it, a complex number. So sometimes you'll hear people say, like, convert to polar form, or sometimes they'll say, like, give it in modulus argument form. Sometimes you'll hear people say that, and they just mean give it in modulus argument form. That means tell me what r the modulus is and theta the argument is of the complex number. We've flooded you with some new words today, so there you go. You have some new vocabulary in your life. Let's try doing a conversion from rectangular to polar form and stuff too. Yeah.
So, like, I get that you said, like, some stuff about imaginary numbers, but, like, as far as I'm concerned, I thought complex numbers, like, didn't exist. So, like, what exactly is the point of doing all these math things with numbers that aren't Like, what does it accomplish?
Yeah, let's talk about that one later. I have a lot of, you know, like I'm ready with a 45-minute speech about that. You know I am, right? I have a lot to say about that later. I'm sure, yeah, ask again tomorrow on a day when we don't have 3 minutes left. I have like a very long prepared speech for you.
So then we can like further check our line of like, we're trying to measure to what extent we are.
I don't think you need a calculator for this. Go ahead and find r, find theta. In the end, like what I'm asking, I hope it's clear, is I want you to write it in this form, right? Something times cosine of an angle plus I times the sine of that angle, right? Fill in these blanks, right? And then we'll be done. That's what we're looking for. What's the modulus and what's the argument of this complex number? Yeah, what's r? What's theta? Figure it out.
But then I can't calculate that.
Wait, do you have to solve it with your cheese, or can you just say cosine of the angle?
What's the angle? Yeah, maybe you can just name it. What does r come out to be?
320 root 2.
Is that cool? Can we just say 320 root 2? You can work through the algebra if you like, right? Is that cool?
Oh wait,
Yeah.
negative 320.
And then what's theta? Is it obvious what quadrant we're talking about? Just look at where the point is, negative. So we're talking about the third quadrant, and they're equal distances. Maybe can you, without the calculator, I think we can just do this. What is the angle we're talking about? Yeah, 5 pi over 4. All right, so I think we're ready. We just drop these things in here. 320 root 2, and 5 pi over 4 goes here and here. All right, so that is polar form. Let's just check here. Does this make sense? Is this still exactly equal to what we started with? I think it is, right? What's cosine of 5 pi over 4? Isn't it negative 1 over root 2? That times 320 root 2 is clearly negative 320. So this is still the same the same complex number, right? Like if you multiply it out here and work with it, you get the thing we started with. It's not surprising, I guess. It's just a different way of writing it that reveals r and theta. Okay, I guess we're done. Huh? You will be just fine on homework 6 tonight. Please make sure your trash gets in the big trash can here. See you tomorrow.